Okay, so welcome back to another video. So here we have the infinite product series of 1 divided by 1 minus tangent square of 1 divided by 2n. So anybody that's, when we're dealing with product series or even summation series, you would want to expand a series out to get some sort of pattern, whether it might be that by slight chance that actually some terms would cancel out of that. But this actually might be proving a little bit difficult just doing that. So generally, as a sort of a backup case, or rather as an alternative, you could put it this way, you would want to find some sort of generalization for such the series you're integrating. Even the same thing when you're dealing with either integrals as well. Any sort of functions in general, really, to be honest, with that expansion. So that's probably the takeaway of how we're actually gonna do this. So we're actually gonna find our nice general closed form, and it actually simply comes down to just afterwards. Once finding that general closed form, we can actually just plug in a single value, and then we actually can achieve the value we want from said generalization. So this is actually going to rely on specifically utilizing the double angle formula for the tangent function. As you notice, we have a tangent function inside of our series. We're actually expanding the product series up. And there's a little bit of calculus involved along the way utilizing some limits. And it's going to be a fun one. So why don't we actually just jump right in? Of course, this is actually good to note that what is the formula for the double angle identity for the tangent formula, which says that this is tangent of 2x is going to be equal to 2 times tangent x, and then divided by 1 minus tangent square of x. So with this being the case, why don't we actually replace this with a different input. Let's just say we divide this by 2, so we're just left with tangent of x. So that means all the inputs for the 2x will be replaced for x divided by 2 for over here. So what I'll write is tangent x, and also keep in mind is the way that it's how it's written, because we actually have a form of some variable and then divided by 2n. So that's sort of speculation saying that we can actually write this a little bit differently to say that tangent x is the same thing written as x, or written the same thing as tangent of x divided by 2 to the power 0. And that, of course, can be rewritten as if you just, as mentioned, just replace the different inputs for this. So this is going to be 2 times tangent of x divided by 2, and then all this divided by 1 minus tangent square of x divided by 2. Okay, so why don't we move on to the next number? So we have tangent of x, and then, so now in this case, we'll let this be 2 to the power 1, so x divided by 2. In other words, so 2 times tangent of now x divided by 2 to the power 2, since it's just divided by 2 yet again, so I'll just keep that in that similar notation. All divided by 1 minus tangent square of x divided by then 2 to the power square. Then why don't we move on again? So we have now, we actually just keep going, expanding this a little further. So we actually now have that continuing forward. So I have now, let's say we have tangent of x divided by 2 to the power n minus 1. So now that's actually written the same thing as 2 times tangent of x divided by 2 to the power n, and then divided by 1 minus tangent square, and then x divided by 2 to the power n. Now, we can continue going on, so on, so forth, if we want to continue expansion, if we want to, but there's actually no need for that. Here's a little something of some observation you want to make. So we have something of 1 minus tangent square of some x. We'll disregard the 1 and leave that as a variable. So we have something in this similar fashion over in the denominator. So why don't we actually get this by itself? And so we have something of an easier formula that we can actually, expand this out to. So in other words, if I left this by itself, I have 1 minus tangent square of x divided by 2 to the power n. So that would have to mean that that's actually just 2 times tangent of x divided by 2n, and then all this being divided by tangent of x divided by 2 to the power n minus 1. So close that off. So that's have something, but we have similar. So of course, this is actually just a reciprocal. So we'll only actually take the reciprocal of all this. So 1 divided by 1 minus tangent square of x divided by 2 to the power n. Then take that reciprocal over here. So that means I have tangent of x divided by 2 to the power n minus 1, and then divided by 2 times tangent of x divided by 2 to the power n. Now, doing both sides, we actually take the infinite product series. So that means the infinite product starting with n is equal to 1. So 1 divided by 1 minus tangent square of x divided by 2 to the power n. So this is actually the generalization we want to follow. As you notice, we're actually going to let x equals 1 to this case as to get our final answer, but we'll get to that step once we find this generalization. So that means I take the infinite product series over here on this side too. But let me actually let the right side, we're going to write this in terms of a limit. So I'll let the limit as capital N approaches infinity. So I have the finite product series, our upper index is n, and then lowercase n is equal to 1. Up now we have tangent of x divided by 2 to the power n minus 1, and then divided by 2 times tangent of x divided by 2 to the power n. All right, so now that just leaves the right side. So we can actually just avoid this limit right now. Then let's actually expand the finite product series out. So if I expand this out, so let me actually denote this in a different color. So if I expand this finite series out, so now if I do this for each term, so that means I have now tangent x, then we divide this by, so this is 2 times tangent of x divided by 2. Then now we multiply, so that's the n equals 1. So now let's do the n equals 2. So tangent of x divided by 2 divided by 2 times tangent of x, and then divided by 4. Now, if let's try another one, so that means now tangent of x divided by 4, and then divided by 2 times tangent of x divided by 8. Now, if we can actually just continue on, so on and so forth. So let's see, the last two terms, I have tangent of x divided by 2 to the power n minus 2, and then divided by 2 times tangent of x divided by 2 to the n minus 1. And so the last term I'll write one more is we have tangent of x divided by 2 to the n minus 1, and then divided by 2 times tangent of x to the power 2, or x divided by 2 to the power n. And so with that being the case, you'll notice some things are going to cancel out. So the tangent of x divided by 2, so that's going to get rid of itself. So that means tangent of x divided by 4, same thing. Then the tangent of x divided by 8, so on and so forth. Then that's going to cancel here. That's going to cancel. This is going to cancel. And so we're left with just a bunch of tangents over here, tangent of x, and then all being divided by tangent of x divided by 2 to the power n. And then we actually have a repeated amount of 2's under the denominator. So we actually write this in terms of an exponent. And so we can actually just deduce this down to say that we have the limit as n approaches capital infinity of, now this is going to be tangent x, and then divided by, so the repeated amount of 2's to the capital N amount of times. So then, and now multiply by, so tangent of x divided by 2 to the power capital N. So my mistake that I should have changed this instead of lowercase n to supposed to be capital N. So let me actually fix that error first. And now our limit for this, of course, so tangent x can go outside because this does not depend on our capital N. So we have tangent of x multiplied by the limit as capital N approaches infinity. Let me actually write this a little bit differently. So this is going to be great. So this is going to be written as 1 divided by 2 to the power capital N. And then under that fraction, we're going to have tangent of x divided by 2 to the power capital N. Okay, so with that being the case, so now we actually have to focus on this limit over here. So let me actually put this on the side. And what we're going to do here in this case is that we're actually going to do a little bit of a substitution. So over here, we're actually going to change this in terms of u. So why don't we let u equals 1 divided by 2n, capital N. So that being the case, so that means as n approaches infinity, that means u is actually just going to approach 0. So now we have that our new limit is going to be u approaches 0. So replace this, I have u, and then divided by tangent of, so that means this is going to be u and then times x. Okay, so now I take that limit. What we have is that this is in terms of a 0 over 0 indeterminate form. So that means I can apply L'Hopital's rule, take the derivative of the numerator and the denominator on its own. Now, do not use the quotient rule. Be careful with that. So now if I take the derivative, so that means this is going to be the limit as u approaches infinity, or 0, of 1, and then divided by, so derivative of tangent is secant square of ux, and then take the derivative of the inside, that's just going to be x in respect to u. Keep that in mind. So I have x and then secant square of u times x, and of course take that derivative again, so that means secant square is actually just, all this is actually just going to approach 1 divided by x. We're just only putting this in u. So that means now this actually just reduces down to just tangent of x times 1 over x is equal to 1 or tangent of x divided by x. And that is actually our final generalization closed formula. So let me actually denote the arrow over here. So this over here is going to be equal to this here. And so the last thing is that the whole thing is that we want to solve this. So we have that this is actually set x equals to 1. So that had to mean that if I plug x equals 1, so that means the final answer is that this is actually just going to equal just tangent of 1. And so with that, that is our final answer to this expansive, well, I think that's the wrong term to use. What we have is that that's our final answer to this crazy infinite product series relating with the tangent function, just like that, with a nice generalization that we saw for with this pattern utilizing the double angle identity of the tangent function. So yeah, that's pretty cool if you ask me.